So my name is Sean. I am a first-year graduate engineer at the Water Corporation. Today I'll be giving you a snapshot of the project that I've been working on. That was my thesis about 3 years ago. So I'm sure everyone in this room, most if not all, have dealt with corrosion in one form or another. And it's a very prominent problem all across different engineering industries. And it's a natural phenomena, so that's okay, until you get problems that look like this. So bursts like this cause safety issues. It's a burden on society, resources, and finances. So the balance that we want to have is, well, spectacular failures of our assets like this versus longer running times of our assets. So the photo, or the animation that I have on the screen is actually a burst in Melbourne. It wasn't actually due to pipe corrosion. I chose it because it's a spectacular failure. And not to say that corrosion cannot cause bursts like this as well. And I'm not sure how many of you recognize the photo on the right. It's actually Old Faithful Geyser in Yellowstone National Park. And believe it or not, the heights of these are comparable, about 30 meters in height. So about 3 years ago, I was taken on by the Water Corporation to investigate corrosion in a special type of pipe, these water bores. And they're a very important asset. They're a critical water source for the regional areas in WA. And the deeper bores that go about 1 kilometre below ground in the Yarragadee aquifer, they can be very expensive to re-drill. And it is believed that pitting corrosion is the predominant failure mode for these bores, and that was confirmed through my research. So my goal became to develop a remaining service life model to predict the remaining service life, a remaining service life model for pitting corrosion, and also to investigate inspection technologies that we can apply to water bores. So for those of you who are not familiar with pitting corrosion, it's a very localized form of attack on the surface of the casing. So it creates cavities in the steel rather than creating a uniform layer of rust. And if we divide our steel casing into discrete layers, as shown in the diagram, and give each layer a number, we call these states, then we can describe the pit depth as being in a particular state. And so the process of corrosion now becomes changing from one state to another. So this is the beginning of a formulation of our model. And this can be described using a Markov process. And a special property of a Markov process is that it's memoryless. And what this implies is that, or the outcome of this, is that we can predict the condition of our asset in the future using data that we can collect today. So we don't need to know the process history, how it got to where it is today. All we have to do is take data, feed it into the model, and theoretically this model should give us a remaining service life. But how do we know when these transitions are going to happen? So the next thing we have to formulate are what we call transition probabilities. So that the probabilities that a particular pit is going to change from one state to another in a certain time frame. So this slide here is supposed to illustrate how this model works. So here we have, we'll pretend that we have a casing that's 30 years old. We've done a scan and we've collected the data and we've created a histogram. And this histogram, all we've done is fitted a curve to it. So we can say that the majority of pits are between 2 and 6 millimeters deep. And just assume that our wall thickness is 10 millimeters, so anything past 10 is equal to penetration. So this is what our pit depth distribution looks like at 30 years. But before we can say when the remaining service life is, we need some sort of threshold. So when do we say enough is enough? And this depends on the user's risk tolerance. So for the purpose of this example, we'll say we're interested in all the pits that are over 6 millimeters deep. So if we take a sample of our casing, that's a top view, and we can highlight all of the pits that are over 6 millimeters deep. So that's what it looks like now. That's what it looks like in 10 years' time, and that's what it looks like at 50 years of age. So we can see here we have pits that have corroded all the way through the casing, and these will be part of this bit over here. Okay. So this, I programmed, or I developed this model in a program called Mathematica, and then I transferred it from Mathematica into an Excel spreadsheet programmed in VBA, or Visual Basic. So this is the interface that we use. There are parameters here that I don't have time to explain in this presentation, and this is the output using simulated data. So I didn't have real data to work with. All I could do is guess on what I expect the data to look like. So I fed that into the model, and these are your outputs. So this graph actually matches this interface. So my perforation, my threshold was 10% perforation. So you can see this blue curve propagated all the way to the red curve, and perforation is at this point. So 10% of the curve you can't see. And this equation at the bottom here is the governing equation. This is what gives you these curves. And don't worry about what this means, but you can see here that it depends on time. So as you increase your time, this blue curve will move towards the red curve, as I illustrated previously. And a couple of the other parameters, RS and CS, they're environmental parameters that affect the rate of corrosion. So the next logical step is, how do we collect this data? And because there is no specialized technique in the water industry for taking measurements in bores, I had to investigate the oil and gas industry. And went to companies like Schlumberger, Baker Hughes, Halliburton, Plus, and they have great inspection technologies, but they're prohibitively expensive to us. And not to mention the risk of contamination from using their equipment in our aquifers. So actually at the beginning of this year, I started with the field services branch in the Water Corporation as a graduate engineer. And one of the first things that happens is I get pulled back into this project because the Water Corp decided to build their own rig. So this is a schematic that our design engineer came up with. We have here the top side, which consists of a control room, recording software, and the computer that goes through a demultiplexer, which basically decodes the signal sent from the bottom side. So you have your optical fibers and your winch that goes down to your rig. So inside the rig you have a multiplexer, which sends the data through a single mode optical fiber, your batteries, encoders to tell you the position, and you have your data collection unit and probe, which is shown in this picture on the right here. And this unit was purchased from a company called Edify. It's a single investment that we've made. Is very expensive, $130,000, and we have licensing fees every year as well. So it's a pulsed eddy current technology. So what is next? This rig is being built at the moment. So we received this unit in mid-October. So it's still in the process of being designed, and after design we're going to do a bit of testing, trialing on non-production bores, so monitoring bores that we no longer need to use. And we also need to understand the data that comes out of this bore, so we need to do a bit of data interpretation basically, because the data we feed into our model is very important. So if you feed it rubbish in will give you rubbish out. And after we have interpreted the data, we also may need to calibrate the model. So calibrate the model to give us an as accurate prediction as possible. So we also want to understand the probe, the behavior of the probe under different circumstances. I've already done a bit of work on that. And as a far-off extension, we also want to expand our capability to do pipe inspections in general, especially cast iron mains. We've already tested a handheld unit, so this was a custom-made unit. We also purchased a handheld unit that we can use in the field every day. We've done some scans on cast iron. It does give us a result, but because it's not designed for cast iron, it's designed for carbon steel, the results are not accurate. So they're precise but not accurate. So we need to do a bit of calibration and data interpretation there as well. So thank you very much.